In this video on 9.6 Modeling Real-World Data, we're going to review how to figure out the type of data you're looking at based on linear, quadratic, and exponential data analysis techniques, and we're going to introduce a new one compared to what we already have done in our class. So square roots, that fits for this chapter because that is the inverse of quadratic, and we were covering that in section 9.5 and in section 9.4. So let's go over this. For linear, it's constant first differences between the y values, and that's for evenly spaced x values. Then you go over to quadratic. So that's differences on differences. When those are constant between, again, consecutive y values for evenly spaced x values. All right, let's we've only worked in one chapter on exponential, so let's definitely review this one again. You have constant ratio, or ratios, between y values for evenly spaced x values. So when you divide, let's say, the second y coordinate by the first y coordinate, and then you do that for the next pair of consecutive y coordinates, overlapping, of course, so then third on the second and fourth on the third. If they all have approximately the same ratio, exponential, because you're working backward and you are saying, what did I multiply to get from one term to the next? And that's where the exponential comes in. Now, square root. Think quadratic, but given equally spaced y coordinates, you have second constant differences between x values in your table. So that's the first row. And that's what makes square root different from all the others. So it's easy to spot. Whenever you are given equally spaced y values, it's a pretty good indication that you're going to have square root, but you always want to check for second constant differences between the x values. So let's take a look at our first example where we have time versus population, and are our x values equally spaced? Yep, so that's good. Constant change in x is 4, so delta x equals 4. Now, quick glance, like, all right, so we're decreasing. Like, you get an intuitive feel for a little bit, but also, hey, it's population. So my gut instinct is we're looking at exponential here. So I'm going to take the second y coordinate divided by the previous one, and I get equal 0.96. And then I'll take the third over the second. So in doing so, I'm asking, really, what number or what base in the exponential equation am I using to multiply to get from one term to the next? Right now, it's looking like a 0.96 base, so exponential and specifically decay. So this population is waning. So it's getting less. So I'm going to try one more. 3 times a charm. And this one, approximation symbol, it is about 0.96. So that's close enough. Now, one of the things that will be stressed in this lesson is that in the real world, numbers hardly work out like theoretically as would be predicted. So you got to consider that things can be close enough just to point you in the right direction, that since we have ratio of consecutive y values being approximately about the same constant, then we get the fact that this is an exponential model will fit this data pretty well. You get a really nice r squared value. So let me make room for the next problem. Notice we have equally spaced y values. So their delta y is 1. And then we are going to study the change it takes to get from one term to the next between the x values. So from 1.6 to 3.6, adding 2, and then 2.8 0.8 for the next pair, followed by 3.6 and 4.4. Now, none of those were constant, so it's not linear. Didn't think it was going to be anyway, but now we can do differences of differences, suspecting this is the inverse of quadratic, so square root. So difference here, 0.8. Next one, 0. Okay. And, yep. So what this means is square root. Moving on. As I advertise, real-world data rarely have differences or ratios that are mathematically constant. So still analyze to see if they are close to constant, then that gets you started on where you should select among your list of regression models on your calculator, for example. So write a function that models the data. Flyers printed and the amount of profit that you actually get in based on that advertising. Let's see here. Do I even have equally spaced X values? I do. That's kind of another thing, is that they may not be perfect. Like, you may miss a year in your survey. So, I mean, you kind of still go with it, though. Profit. Constant ratios, because that's quick to check. 7 on 10 is 7. 175 on 7. Nah, I don't think so. So let's do the constant differences. First up, 60. Next, 105. Let's continue down the line. And not linear. So these are not directly proportional. As the number of flyers printed increases, the profit also increases by a constant factor of k. Nah, not slope and all that. So let's do differences of differences. Yeah. Real world's not perfect, is it? Close enough. It's worth a shot. I'm going to go ahead to try quad regresh. And then I will assess from there if I have enough information to really say that it's a quadratic model that best describes this table of data. Well, do the quadratic regression on the calculator. Profit for number of flyers printed will be approximately, the regression model would be 0.002 f squared. It's quadratic, so you got a degree of 2, plus 0.007 f minus 11.2. Guess what? The r squared value was? Yep, it was about 1. So even though these really aren't that close, I mean, in the grand scheme of things, we're working with numbers like 600 and 720. And these numbers here are varying at most 32 to 51. So about 20. So relatively, they're close enough. So this would be our quadratic model, and this is the work to show why we chose quadratic. Now you could always choose higher degree models like cubic regression. But the higher the power you go, the more variables you introduce to the system, and the harder it is to isolate things. So you always want to go with the degree of the model that is the lowest. That seems about right. Next example. So again, year and population. I'm going to think exponential. I mean, you could go after constant differences, but it's population, so I think that's a fair assumption to start with anyway. Won't always be exponential, but let's give it a shot. So the second, let's see here, constant, equally spaced x values, 3, 4, 3, 2, 3, 1, that's horrible. It's real world data. I'll take it. I mean, like, let's say this turns out to be exponential growth. Voila. And then, yeah, it's not going to be a smooth curve like that. Like you're going to have points here, 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 and their spaces x, y's are not going to be the same distance apart here, and that's okay actually. It's really just one of the assumptions for making the constant ratio thing really work, but it's flexible. I mean, they're close enough. Like again, we're using these like really large numbers, so let's go with it. We have second one 490 over the first one 400, giving approximately the ratio of 1.23. Again, 642 over 490. Remember, I'm asking, what do I do to multiply to get from one term to the next? So then that's why I am actually dividing the second term by the first one to undo that multiplication, to reveal what it was, if it was in fact exponential. So this next ratio gives about 1.31. All right, I'm in the vicinity here. So let me do one more. So 787 divided by 642. 1.23. I'm buying. Okay, let's try exponential and assess the r-squared value. Remember, when working with years, let's set 1990 to year 0. So years since 1990 is how we'll read this. So 3 and 7, etc. So I'm going to put in those values into the calculator, and I get a exponential regression model. The population for year Y, and that's going to be for years since 1990. We get approximately 399.9 times the base of 1.07. So that's growth. It's good. If it's like people or endangered species. And what do we got here is approximately 1 for that r-squared value. So this actually worked out, even though we did not have equally spaced y values and we didn't necessarily have mathematically constant ratios.